who are maybe a bit lost, I recap. We are following the evolution of Fourier wave numbers, co-moving wave numbers, a long time, starting from some initial condition outside the Hubble rate. Modes enter one after each other inside the Hubble radius, and they have a different evolution because they are characteristic times: equality between matter and radiation, decoupling, equality between matter and lambda, and today. And we discussed qualitatively the different evolution in each region. We saw that a particularly important quantity is a transfer function of photon temperature at the time of decoupling, because this is nearly what we observe in CMB anisotropies, with correction from minor effects. We showed that outside the Hubble radius at decoupling, that would be this scale, we have a plateau reflecting the flat initial conditions, no evolution in this region. And then we have a series of peaks centered on a curve which is not zero, especially because of baryons, and with some diffusion damping, such that the amplitude go to zero at large scale. And from this, we could infer the qualitative shape of this temperature spectrum expanded in harmonic space as a function of Legendre multiples L. We explain one by one these effects: the Sachs-Wolf contribution, the Doppler one, the integrated Sachs-Wolf, late and early, corrections from diffusion damping, which are these suppressions here, and from rayonization. Okay, so now we are going to apply this to a particular model, which is minimal lambda CDM. And of course, in your research, you might be more interested in deviations from this model, but it goes beyond this course. At least if you can understand the basic picture, you can easily then get its generalization to other cases. So in the minimal lambda CDM, which is really the minimal model fitting most observations today, it's assumed to be flat. Otherwise, it would be called open or open lambda CDM, or closed, sorry. It has 6 free parameters. So let us review quickly these parameters. First, we assume that initial conditions produce a power law spectrum, and because inflation predicts a nearly flat spectrum, we only include first-order correction from this flatness. And so we write the primordial spectrum of curvature perturbation as an amplitude times a tilt. K0 here is a pivot scale. It's an arbitrary scale at which you decide to define your amplitude. NS is the tilt. Some inflationary models predict NS a bit larger than 1. Most of them predict a tilt a bit smaller than 1. If it was exactly 1, we would have an exactly flat spectrum. This would be the Harrison-Zeldovich model. I recall that H0 can be written in terms of a dimensionless parameter small h, and these are kilometers per second per megaparsecs, with h of the order of 0.7. And finally, when we talk of physical densities today, we will use the parameter small omega. So those who are doing a lot of cosmology know this small omega. For the others, I recall that I can write this physical density today as the big omega parameter for the species X times the critical density today. But the critical density is only a function of the Hubble scale. And so you see that I could write this number as a fixed number with some unities, say gram per centimeter cube, which depends only on the value of the different constants and units, times big omega x times h squared, and this is what we will call small omega x. Okay. So physical densities are parametrized by this dimensionless number small omega. Now, the parameters of lambda CDM are the following. We have 2 parameters for primordial perturbations, the amplitude and the tilt. And these are supposed to be predicted by some inflationary model. Then we have three parameters concerning the composition of the universe. And at this stage, you are free to make several choices of parameter. You can take different bases of parameter. And the one that I will choose is the one which makes it most easy to decompose the effects on the CMB. This basis is omega b for the baryon density, omega m for the total matter, non-relativistic matter density. So these are baryons plus CDM. And next, what could I put? I could put omega gamma, density of photons. It's not a free parameter because we measure the CMB temperature today. Omega gamma is fixed. Next, I could put omega of neutrinos. Now, first, neutrinos today, if they have a very small mass, have a very small density. Moreover, because neutrinos play a role which is both small and complicated, I did not mention neutrinos in this course. Okay? I would need 2 more hours, at least. So we neglect neutrinos, but by doing so, we are not doing a big mistake. Okay? So I don't put omega neutrino here, which in principle would depend on the neutrino masses. I could put omega of lambda, the density of a cosmological constant, but I would have a problem that only some particular choices of my small omega would respect the assumption of a flat model. So I prefer to put big omega lambda here. And if I do so, I can always assume that this model is flat if I satisfy the constraint equation omega m plus omega lambda equal 1, which imposes that h is a derived parameter, because I can write h as small omega, square root of small omega divided by big omega. But big omega is 1 minus omega lambda. So I don't need to add h as a free parameter. It's already included in this parameter basis. So these are the parameters dealing with the composition of the universe. And the last one is the optical depth of rayonization. 2 days ago, we saw how to define this optical depth. Okay. And this parameter can be said to be an astrophysical parameter. In fact, it's very difficult to predict, to make a model for predicting tau rayonization, because star formation is a mess. It's very difficult to model. So people would say that it's not even an astrophysical parameter, but a gastrophysical parameter. It's a famous joke of Dick Bond from Toronto. Oh, yes? Yeah, it's a number. So what you mean is that rayonization is not a number. Rayonization is a function of how much the photons emitted by stars rayonize the medium, the intergalactic medium, at a given time. So it's a function of z. Tau is an integrated quantity. It's the integrated optical depth up to some point after rayonization, from here to after rayonization. Then it remains constant. And your question is relevant because the CMB sees a little bit more than tau rayo. It could see some of its characteristics, but it's very difficult. And with WMAP data, all what we can learn about rayonization boils down to this number. With very precise experiments in the future, probably this parameter basis will not be sufficient. Okay, yes?
So this, we assume omega m plus omega lambda equals 1.
Omega matter plus omega lambda equal 1, yeah. Flat universe. Do you find this annoying? Or?
No.
Okay. Yes? Between, it's given here. Small omega is big omega h squared. Yeah. We will say a word about what changes when you add curvature, because actually it's quite trivial. In half an hour from now, it will be quite trivial to say the impact of curvature. So now we recapitulate the evolution of densities in lambda CDM. So here we have rho, the densities. We have A. It's always assumed to be logarithmic plots. And if you are picky, we can divide by A0 in order to remove the arbitrariness in the choice of A0. Okay, so the first density which dominates at early time is the one of omega r of radiation. And for us, radiation is photons. If we had more time, we would discuss the effect of neutrinos. And if neutrinos were assumed to be massless in first approximation, they would contribute to this rho r. Okay, the density today is fixed by the measurement of the CMB temperature, 2.725 kelvins. So this curve is completely fixed at any times. We know its value today. We know that back in time it scales like 8 to the minus 4. Okay, the second contribution is that of non-relativistic matter, baryons plus cold dark matter. It's something like this. So this is rho matter, where M is B plus CDM. And today, the free parameter governing the amplitude of this curve is omega M. If you fix omega M, you can extrapolate back in time because this goes like 8 to the minus 3. And the last curve is omega lambda. This amplitude is fixed by big omega lambda h square. So it's a function of my free parameter. I could use what we wrote here. Okay, it's a bit complicated, but we will not use this combination. Okay, it's fixed today, and it's constant back in time. And automatically, I see a few characteristic times appearing. The time of equality between radiation and matter is here. And in my parameter basis, you see that it is uniquely determined by omega m. The white curve is fixed, the red curve moves with omega m. So the redshift or the scale factor at equality can be derived in one line as a function of omega m. So omega m is like the knob moving this leftward or rightward. Same with this time, the time of matter lambda equality. In this case, my knob is omega lambda. Larger omega lambda means equality earlier. Okay. The time of recombination takes place somewhat after the first equality. And we will consider it as fixed by the thermodynamics of recombination. At the next level of precision, we would point out that the time of recombination has a very small logarithmic dependence on the primordial helium fraction or the baryon density, but this is very small. So let us consider recombination as taking place at a fixed temperature, meaning fixed redshift, with respect to today, meaning fixed scale factor. Okay. Now we are going to review the effects on the CMB. So we will have 6 effects, 6 like degrees of freedom affecting the shape of this curve, and we will call them C1 to C8. So C1 first is the uncertainty on the peak scale. I'm referring always to the harmonic spectrum. So when I say peak scale, I mean at which L do I see the peaks. So peak position would be more intuitive. Let me call it peak position. Okay, do I have some freedom to fix the position of all the peaks independently from each other? No, because as we said, these are all harmonics of a single characteristic scale in real space. So all these peaks can move together to the right or to the left, but this is controlled only by one quantity. What is this quantity? It is the sound horizon at decoupling. I write like this. I could put Z of decoupling, A of decoupling, time of decoupling, whatever. Okay, it should be clear from yesterday that this is a scale which determines the scale of the peaks, the phase of the oscillations. Yesterday we had some cosine of K, CS, eta in our simplified solution. What is this argument? In fact, it is K times the sound horizon. So here it's in co-moving scale. Co-moving sound horizon that I call RS. RS is the sum of dt over A times CS of t. You get from here to here in the limit in which CS is nearly constant. In this case, you can factorize it out, and this is eta. If CS is not exactly constant, this is only an approximation of the true result, which would be KRS. So really, it is this scale which controls where you find the peak in Fourier space. But we don't see the peaks in Fourier space. We see them at a given multiple because we project Fourier modes on the last scattering surface to some angles. So in fact, what we see is the scale of the peak, theta peak, equal to the sound horizon at decoupling divided by the angular diameter distance to decoupling. And this is nothing but pi over L of the first peak. Okay, this is the important quantity. On the numerator, I have a number which depends on the evolution of the universe prior to recombination, decoupling. Since in an integral between early times here and decoupling. On the denominator, I have on the contrary quantity depending only on an integral between us and the last scattering surface. What are the parameters controlling this? In this integral, you will have a dependence first on omega baryon, because remember that omega baryon enters into sound speed. There was an R parameter. So this depends on omega baryons. Next, when you integrate, the function A of t is important. Is the function A of t completely fixed before recombination? No, because we don't know when equality took place before recombination. So if you move this point to the left or to the right, you change your solution for AT, you change your integral. So since the time of equality matters and is tuned by omega m, there is also here a dependence on omega m. On the denominator, you only need, in order to compute the angular diameter distance, to integrate background quantities between today and recombination. The only freedom is in the time of matter lambda equality. So the only important parameter here is omega lambda. At least in this parameter basis that we choose, we can do this clear decomposition of the effects. Yes? Yes, for me it's the same thing, recombination and decoupling. So physically, it's because electron and baryons recombine that photons decouple. They obey to slightly different definitions. So decoupling is the maximum of the visibility function. Recombination you can define as the time when 1/2 of the electrons are recombined. So you will find slightly different number, but they move together with each other. And for me, this is the same thing. Yeah. Okay. The second quantity controlling the CMB shape is the ratio between odd and even peak amplitude. This one is fairly easy. Remember that in order to compute the power spectrum, we took the square of the transfer function. And because the 0 point of the oscillation was shifted, when you square this function, you get a large peak here, then smaller, then larger, then smaller, etc. So what controls the ratio between even and odd peaks, especially the first ones, because after it equilibrates, is this curve, which is determined in our solution of yesterday by 1 plus r psi. What is important is the r. In the r, the baryon density is hidden. R is a ratio of baryon to CDM density. So this ratio is controlled by the ratio of omega b over omega, R is a ratio between baryons and photons. Okay? So this is omega b over omega lambda, photons, gamma, but this is fixed. So it is omega b which controls the density of baryons, which controls this asymmetry in the peaks. Okay. It's a very distinct effect. So it means that omega b is maybe the easiest parameter to measure with the CMB maps. Next, C3, this one is a bit more subtle. It's the overall amplitude of all peaks. Okay. Remember what we said yesterday about, and you see that all details matter in this business, about this region here. We said in this region that because the baryon density is significant, the oscillations are decreasing, okay, instead of being stationary. Now, when we change omega m, we move equality closer or further away from decoupling. And this is important. If equality takes place very late, like just before decoupling, there is very little time for the fluctuation to decrease. So they arrive here at decoupling with a larger amplitude. Moreover, if equality is just before decoupling, in this region, the early integrated Sachs-Wolf is enhanced because the metric fluctuations are far from stabilized. And this will enhance the first peak. Fortunately for us, the two effects go in the same direction. If equality takes place later, for these two reasons, the peaks are all shifted upward. Okay, especially the first one, because the first one is the most sensitive to the early integrated Sachs-Wolf. If equality takes place very early, there is a long decreasing phase. The metric fluctuations are already completely stable at recombination. I lose also my early integrated Sachs-Wolf, and the peaks are much lower in this case. Okay, so the overall amplitude of the peak depends on the duration of the stage between equality and recombination, and depends on the early integrated Sachs-Wolf effect. And this is controlled by omega m. Let's try to be more concrete. Let's do the following reasoning. Omega m increases. If omega m increases, the red curve goes higher. Equality takes place earlier. So there is more damping of the fluctuation because the stage is longer stage, longer intermediate stage, and the peaks go down. But this does not affect the Sachs-Wolf plateau here. It's only about the peaks. Okay. Now we are left over with the easiest effects. C4 is the damping envelope at large L. What controls? So when you see the peaks, you can easily guess the envelope here going through the maxima. Can this envelope move to the left or to the right? Yes, because it is controlled by the diffusion length at decoupling. as we said yesterday. So it's a bit like the peak position. Again, we are speaking of a position here. What the quantity which is important now is the diffusion scale at recombination or decoupling. It's a quantity that we called RD, computed at decoupling. We showed this integral when we talked of a random walk, you remember. We defined the comoving diffusion length at decoupling. I want to know under which angle or which L I see this scale. So I have to take a ratio like here. I need a physical length here. So I multiply by the scale factor at decoupling. This gives me the physical diffusion length at decoupling. I divide by the angular diameter distance to decoupling. And this gives me the angle theta d corresponding to some pi over LD, which corresponds to the characteristic scale at which there is an exponential cutoff. And in fact, this envelope can be modeled in first approximation by an exponential cut in my C of L. This exponential cut is like L over LD squared. And this LD is precisely this one. Okay, so how does this depend on lambda CDM parameters? Here in RD, if you look at our expression, it's an integral. It's a bit like this. It was the integral of over d eta of 1 over A n E sigma Thomson. This was RD. Okay, if we consider that the recombination history is completely fixed by some particle physics equations, then the only degree of freedom is A before recombination. A before recombination can change only, as we say it here for this quantity, because we don't know the time of equality. And it will change this function of time. So the numerator is controlled only by omega m. I realize that in my notes it looks cleaner, so good for you because you have the notes. So there is only omega m here. And on the numerator, it's the same angular diameter distance. It's omega lambda which controls. Okay. So these two quantities look the same a bit. They are controlled almost by the same parameters. In particular, if I had the same quantity on the numerator, the two effects would be degenerate, and I would not distinguish. But look, if you change omega lambda, you change dA in both cases. It means that you move the whole spectrum to the left or the right. However, if you change omega m, for instance, it impacts differently the sound horizon at decoupling and the diffusion length at decoupling because they come from very different integrals. And so it makes sense to make the difference between these two. And the last effects are infinitely simpler. C5, the overall amplitude of the spectrum, of course, depends on AS, the normalization of my premodal spectrum. If I change it, I move everything upward or backward. Okay. Remember that the C of L, we saw a formula in which the C of L was a convolution of the square transfer function by this spectrum. So AS squared is a multiplicative factor in the result for C of L. C6, is a companion effect. It's the overall tilt. Because of the same convolution, if I tilt my premodal spectrum by playing with NS, I tilt the whole shape of the C of L, almost like with the power law factor, multiplication. Okay. C7 is the tilting of the Sachs-Wolf plateau by the late integrated Sachs-Wolf effect. I recall you that the late integrated Sachs-Wolf effect corresponding to this bending here comes from the fact that the metric fluctuations are decaying during lambda domination. If you increase omega lambda, this time of equality between matter and lambda will be earlier, so there will be more late integrated Sachs-Wolf, and this will raise a little bit more. So there is only omega lambda controlling this. Okay, and to finish, effect C8 is the effect of rayonization. We said that rayonization dumps all the spectrum by a constant factor above a scale corresponding to the Hubble radius at the time of star formation, and it leaves the left part unchanged. So it's a step-like effect. The step typically takes place at L equal 40. This corresponds to the scale of star formation. So C8 controls the amplitude, the overall amplitude for L bigger than 40. And this is controlled by tau rayonization. Now, we have seen these 8 effects. It's not too much. Actually, I think maybe it's a surprise for some of you who have already worked with the CISOVEL that everything boils down to 8 effects, because when you play with codes, you have an impression that there is infinite freedom and complexity in this curve. Not at all. There is nothing else. But can we really measure all these effects? Well, not quite, because of cosmic variance. Cosmic variance means that we have like a theoretical error bars on large Ls. Okay? And so even if we get very, very good measurements in this region, they don't give us very, very strong constraints on the underlying theory. Okay, so what it means is that the late integrated Sachs-Wolf effect, C7, is very difficult to see. This is why I wrote a small star in front of the effect. Very difficult to see before of cosmic variance. Same with effect 8. 8 is completely degenerate with the effect of the amplitude for L bigger than 40. And for L smaller than 40, I have cosmic variance. So C8 is very difficult to see. It doesn't mean that these effects are completely useless, because it happens that you study models in which the late integrated Sachs-Wolf effect would be so large that then you conflict observation. But what you can, in fact, what happens is that given the value of tau rayonization and omega lambda indicated by other experiments, we believe that these effects are not big enough that we can easily see them, not even with Planck, because of cosmic variance. Fortunately, tau rayonization can be seen better in polarization. We will mention this later. And omega lambda can be probed even by the other effects. It enters here. Okay. So let us forget effects C7 and C8 for the moment. Even definitely. Okay. We are left with 6 effects controlled by 6 parameters. So the system is not over-constrained. You cannot make consistency checks of the model, but at least you can measure all parameters independently. Okay. And this is the case. If you take WMAP data, you plug this model, you get a measurement of all 6 parameters, even without invoking external data sets. Some parameters are more difficult to see. You get a loose error bar on omega lambda, because there are some, given the error bars of the data, there are some partial degeneracies between these effects. But still, you can measure all these parameters independently with WMAP, except that you need polarization to get tau rayonization. Now, what would happen if you add extra parameters? For instance, if you assume that there can be curvature in our universe, a small omega curvature, then what changes is only the late time evolution. Because you are putting another curve here, which is like the effective density of curvature that you can define easily from the Friedman equation. It's negligible at early times, so until recombination, nothing changes, but it changes the late time evolution. Where does the late time evolution appears in all this business? In 3 places. In the angular diameter distance here, but it is in fact the same, and in the late integrated Sachs-Wolfe effect. So if you assume some curvature, it's not that there is a new physical effect, C9. Okay? This is still sufficient to describe everything. But you have one more free parameter controlling the same number of effects. And then you go to 7 parameters with 6 effects, and the CMB alone is not sufficient. And this is why WMAP needs external information from direct measurements of age or BAOs in order to get the spectacular constraints that you know on the smallness of curvature in the universe. There are many more extensions of this minimal model. Some of them are easy because you can just insert them into this picture, while some other parameters, like a neutrino mass, imply the existence of new effects, C9, C10, that I would need to list, which are model dependent. But I think it's very useful to at least to understand this decomposition. And I'm going to show it now on the computer. Yes?
Maybe for later, but
yes.
The C2, is it related with the baryonic oscillations of the matter power spectrum?
Not really, no. We will comment a bit on baryonic oscillations. The fact of changing omega b does not change much the amplitude of baryonic oscillations, for instance. Well, it should become clear later. Omega b is, but we will see it with the computer. Okay, so, yes. Yes. Yes, but you cannot. Yeah. No, we cannot. You can use different formalisms, but you can never beat cosmic variance. Never. Because it's due to the fact that we have only one realization of a stochastic theory. You can change of basis, do whatever, you will not gain anything. It's a physical thing. What you would need to reduce cosmic variance is to observe a larger sample of our universe. So this is science fiction, but it's conceptually feasible. If we could see the cosmic neutrino background or the gravitational wave background, we would see objects emitted from something like a last scattering surface, much larger than the one of photons. We would see a larger volume of the universe, so we would have many more independent realization of the same probability distribution for each mode. And then we could beat cosmic variance, reduce it, yes. But as long as, when we observe the CMB, I mean, when people do galaxy redshift surveys, they can always say in the future, I will have better telescopes, I can make bigger surveys, see a larger volume in the universe, and reduce sampling variance. With the CMB, it's not the case. You see the full sphere corresponding to the universe becoming transparent. You cannot go beyond. You cannot see a larger region, and this is why you cannot do better for cosmic variance.
One more question.
Yes?
Yeah. So what you are saying is that we have these effects that they give us the CMB power spectrum.
Yes.
And they are more or less 6 effects. So what you are saying is that if we use more parameters than this, no matter what parameter we are interested in, that means that they will be degenerated with these 6.
Not exactly. Well, what I mean is that if you have a model with more parameters, the first question you have to ask is, does it introduce a new effect, or can I describe it in terms of these effects? And it's a very interesting question. So I gave an example, that of curvature. The effect of curvature can still be described with the same number of effects. Then you know that there is a degeneracy, you cannot see curvature with CMB only. if you introduce, suppose I play with the equation of state of dark energy, it's the same. One more parameter, same number of effects. Now, if you play with the number of neutrinos or of relativistic species in the universe, on top of the 3 active neutrinos, you assume more relativistic particles. This means that you play with a number that cosmologists call the effective number of neutrinos. This new parameter will introduce a new effect. So you can still measure it with a CMB only.
What's the effect?
We don't have 2 hours, but I can tell you that, okay, it's a very interesting question. I think poorly understood. Most of the effect of NS can be cast into this, except one, which is the neutrino drag. It's the fact that neutrinos, when they free stream, pull a little bit through gravitational interactions the photons out of potential wells. This effect was understood in a paper of Bashinsky and Seljak in 2005, I think, and it's an independent effect. But they found it, but very few people realize that there is this effect in fact. So this is an example where one more parameter gives one more effect, and you can see it. Yeah.
If I have some crazy idea that omega will change during the evolution of time, during the evolution will it change the thing on its effect? That omega will change during the evolution.
Which omega?
Like the baryon omega, the
Yes.
dark matter omega. If
Yes.
that change, will it change this scenario?
No, omega baryon is a free parameter. If you change it, I mean, I considered...
Change as the evolution of the universe. Change with time.
Change with time. You mean you couple baryons with another species, you have decays. Yeah, absolutely, it changes the scenario. Does it change a lot or not? It depends at what time your baryons would decay into something else. But yes, numerically, these are difficult scenarios to study when one species decay into another one. But there have been many examples studied in the literature. There will be more work in the future. Yeah, it's an interesting direction. You could say that that neutrinos have non-standard interactions, and at some point they decay into a scalar field that will play the role of dark energy. You have you can play a lot with these things, and usually it introduces an effect on the CMB, yeah, because it cannot be summarized by this frame. Yes?
At the time of decoupling, was there any entanglement between all of the figures you left over? And if so, what measure did you put up there? What combination of these parameters did you use to measure?
So I really listed 8 different effects, independent effects. You cannot say that C4 is like a linear combination of C2 and C5. Yeah.
Is there some entanglement measure on the CMB? Like,
Yes. When you measure one parameter on the CMB, you marginalize over all the other effects. So you take automatically entanglements and degeneracies into account. Yeah. Okay, it's not that you take the best fit model and then you vary one effect and you see when you should stop and you do the same with second. You always do a global analysis. Okay, pictures. Boom. Okay. I need to restart it. Okay. So we also have mountains where I live. Okay, so I show you how these pictures are obtained. So there are several numerical codes that you can use when you want to compute this curve. Okay, the first historical numerical code was written by Bertschinger himself. You imagine the honor you had to have him as a lecturer. It was very slow, unfortunately, because it didn't have the line of sight integral formalism that we introduced yesterday. The same code was improved with the line of sight formalism by Seljak and Zaldariaga in 1996. This gave CMB fast. Okay? This was the first fast code. Unfortunately, CMB fast is not anymore maintained, and it's not anymore very accurate. Then there has been COMB in Cambridge, which is the most widely used today. CMB Easy in Heidelberg. And the most recent is the Cosmic Linear Anisotropy Solving System, CLASS, that we made available last year. And it's the one which I would say, although I'm a bit biased, that it is fastest, most precise, and most flexible. Only this. Okay? So if you want to play with these things for your research or just for fun, it's very easy. It's a C code with no external library. You download it, and you are almost ready to run. You pass some input parameters. There is a list of hundreds of input parameters. I only put the one that we are going to vary because they are the one which we choose as our parameter basis. So then you run class times your input parameters, and you see it's very fast. It's done. We print it with a Python utility, and these are the C's of L of temperature. So you see how fast it is. If you compare with, I mean, not specifically this code, I mean, COMB is essentially as fast. If you compare with the time for n-body simulations of nonlinear structure formation, okay, there is a factor of, I don't know, I never computed it, 10 to the 8 maybe. Okay. Thanks, linear theory. Okay. Sorry? It's if you want to use it, we will release in a few weeks, probably in July, our own version of CosmoMC, which we believe is also more user-friendly, which is written in Python. It's a Monte Carlo code in Python, so it's Monty Python. And it will be available very soon. And you don't need to know Python in order to use it, because it's like a black box, and you can use it directly without entering into it.
So what's the data incorporated with this package?
Sorry?
What's the data incorporated with this package?
This is not a question on the CMB code, but on the data fitting routines.
So WMAP and what else data?
We are talking of a Boltzmann code. We are not comparing with anything now, okay? Now, if you want, for instance, this Monty Python that will be released, it has more experiments than CosmoMC, and you can add some more if you want. Okay? But this is a different thing. Yeah. I'm not fitting any experiments here. I want to show you these effects. Okay? So, in each plot, there is a reference model chosen arbitrarily, a solid line. And the dashed line is when you increase one of the parameters on the top. The first one, you increase the amplitude, and it's completely trivial. You multiplied everything by a factor. Effect C5. The second one, you increased the tilt. So ns bigger than 1, you give more power to small scales on the right, less power to large scales on the left. Effect C6, also very trivial. The next one, you increase omega b. I increased it only by a small amount, but I think you can see. The main effect is that by increasing omega b, you have increased the first peak and decreased the second peak. Now, this should be clear from this plot. If you increase omega b, it means that at the time of decoupling, you shift this line further down, further away from 0. So when you will square this curve, you will have a larger first peak and a smaller second peak, larger third peak, and then the effect tends to disappear. So you can see how you change the ratio of the peaks. Okay. And this, as I was telling you, is the parameter most easy to measure with current data. So its effect C1. And there is you can see also another thing. So this was effect C2, right? The amplitude between odd and even peaks. But if you change omega b, you change a little bit the sound horizon at decoupling also. And it's not very easy to see, but there is a little shift in the scale of the peaks. But very little, in fact. Okay, here we have increased omega m. As we said, if I increase omega m, I have a longer stage of damped fluctuations. The peaks should go down, and you see very well how all the peaks go down. So this is effect C3. Shift in A equality enhances amplitude of peaks. Moreover, now this is entangled with effect C1. We have changed the sound horizon at decoupling in such way that we see the sound horizon, that the sound horizon is larger, so it appears on smaller Ls. So the peaks are moved to the left. We have changed also the diffusion scale at decoupling, depending on omega m, in such way that this envelope has moved to the left. There is more diffusion damping. So the omega m controls these three effects at the same time, and it's also fairly easy to extract from CMB data. Okay, next, omega lambda. Yeah, we had not seen it yet. We increase omega lambda. And then, so first we expect a shift in the angular diameter distance to decoupling. That will shift the peak position and in the same way the damping envelope. And indeed, we see everything moves to the left. So this is just a geometrical effect if you want. The physics of the CMB is exactly the same. Nothing has changed up to a redshift of around 1. The CMB pattern, the CMB peaks are exactly the same. The only thing you see here is that we are seeing the same phenomena under a different scale, as if we had put a lens between the CMB and us. However, there is also effect C7, the tilting in the plateau due to the late integrated Sachs-Wolf. And as I was telling you, this is difficult to see. But still, if you go to extreme values of omega lambda, this will be so sharp here that it will be excluded by the data. Okay, and now we have still the effect of rayonization. So until a multiple of about 10 or so, I wrote 40. 40 is when the factor is really constant, but already at 10 you have an effect. Nothing has changed in the Sachs-Wolf plateau, but you have suppressed the amplitude on small scales here. Okay, so these are our effects. Questions before we move to slightly different topics? Yes? Yes, in February 2013, yes. Okay, you put me in a difficult situation because I'm in Planck. So, roughly speaking, if I base myself on forecasts which have been made for Planck since a long time, sometime when you mention the effect of Planck, people are a bit disappointing because typically the improvement on the different parameters depend on each parameter. In average, it's an improvement on each error bar of a factor 2. Now, what you have to think is a load volume in the phase space of the module. If you have, this is a minimal model, but say that Planck, even with a model with more ingredients, if you think that you have 10 free parameters and you improve the error bar on each of them by a factor 2, it means that you shrink the allowed volume in parameter space by 2 to the 10. And in this term, Planck is spectacular. If you say it's an error factor 2 on each parameter, it looks like less impressive, but you should think of this 2 to the 10. More or less, it's the case. Now, of course, what we don't know, if we just better measure these parameters, it will be a bit boring, no? Like now with LHC. There is still a chance that we see some new effect, new ingredients, both in Planck and in LHC, and then it will become exciting. And for this, you have to be patient.
Polarization?
Sorry?
Polarization?
Planck is not so good for polarization. Polarization, because the story is that Planck was competing with WMAP long time ago in the phase of design, and WMAP was not supposed to have polarization, so Planck people focused themselves on temperature. And also, Planck was designed in 94, 95, when the importance of polarization was not fully realized. both WMAP and Planck added some ingredients, some polarized bolometers, in order to gain sensitivity on polarization. But Planck is not a champion for polarization. The major improvement on polarization will come from balloon and ground-based experiments after Planck, very soon after Planck. But Planck will be almost impossible to beat on temperature. It's because the measurement will be dominated by cosmic variance up to roughly L equal 2000, when anyway there are errors growing from foregrounds. So Planck will do like the ultimate measurement of temperature. Yes?
So do you have a comparison of this model with data?
No, I didn't do it. I could have done it, but I thought it was more interesting to talk of the theory. But what is remarked, sorry? Yeah, of course. You can look, you look in any recent paper with WMAP data, etc. So the best fitting lambda CDM model is a good fit. You can see it from the values you obtain, or if you plot the residuals, so the data divided by the best fit, you don't feel that you are missing some effect, at least so far with WMAP. Okay. So this is a good model. Any more questions? Okay. Okay. Am I right that we have 15 minutes? Yes. So we can do two things. We can follow the notes and speak a bit on polarization and tensors that I added in the course in the last minutes on request of the organizers, or we leave it for tomorrow and we attack the matter power spectrum. I propose to attack the matter power spectrum, okay? And we will come back to polarization later. Okay, so what we are going to say is an introduction to the course of Shirley Ho. She will go in the details of what you can learn from large-scale structure. She will talk of bias effects, nonlinear effects, etc. I will just present the very basic picture of the calculation of the matter power spectrum in linear theory. Linear theory is an excellent framework for the CMB. For large-scale structure, it's just a first step, and then you have to work more in order to compute nonlinear corrections. Because, of course, the universe is homogeneous today on much smaller scales than it was at the epoch of recombination. Recombination, sticking to linear theory, is a very good approximation. So, part 3, the matter power spectrum. Okay, so definition. We are interested now in the power spectrum characterizing large-scale structure in the universe at low redshift, today or at redshift of 1 or 2 typically. So we are interested in delta rho. Usually what you measure with a given experiment is something related to the total density perturbation. With weak lensing and even surprisingly with galaxy redshift surveys, what you measure is not directly delta rho tot, but something related to delta rho tot. This delta rho tot comes from delta rho photons plus delta rho baryons plus delta rho CDM plus delta rho nu plus eventually other things. You could have delta rho of dark energy if dark energy has large perturbation, etc. We are interested at late times, so photons today are completely subdominant with respect to non-relativistic matter. Neutrinos can play a role, and actually this is a very relevant topic if their mass is sufficient, but already with the indication we have on the neutrino mass from neutrino experiment, we know that it should play a small role detectable in the near future. But since this course does not incorporate neutrino effect because of time constraints, we will assume that neutrinos are massless and do not contribute today by more than 10 to the 3 or something. Raw dark energy, most models of dark energy predict very small fluctuations today. There will be a chapter on this tomorrow. So sticking to this assumption, we neglect raw dark energy. And we are left with B and CDM. Okay, so we will define delta rho total matter as delta rho B plus delta rho CDM. We will define rho bar of matter as rho B plus rho CDM. And the same for delta M. Delta matter will be delta rho M over rho M bar. Okay, so we are interested in the two-point correlation function of this quantity in Fourier space that we call the matter power spectrum, and that we define already in the second course. And for the same reason, we know that this is given by a Dirac function times the quantity that we call the matter power spectrum. And this is exactly the quantity we are interested in, P of k. We know that P, so it's a function of time. We know that this power spectrum is equal to the square of a transfer function times the primordial spectrum with the notation that we introduced before. There is a 2 pi square over K3 here. You can check the notes of the previous lecture, times this amplitude, times this tilt. Okay, so we are interested in the computation of this matter power spectrum for a given primordial spectrum. And so the interesting quantity at the end is just this transfer function of matter fluctuations. I had some discussion with some students 2 days ago telling me, but for us, this function is a product of a function of k that we call the transfer function and the function of time that we call the linear growth factor or something. This function is not always separable in time and k. Okay? It's separable in some simplified model, but I will not use such a simplification. Perfect. So, this quantity can be observed indirectly in many ways. And this is a duty of Shirley to explain it next week. You can see it indirectly with galaxy surveys, modulo a factor called the bias, or with weak lensing surveys, or with Lyman alpha forests absorption in quasar spectra. There are many techniques, but this is always the interesting defining quantity to which you want to relate your observations. So now we want to see qualitatively what will be the shape of this transfer function. So transfer function evolution. So, yes?
Maybe, as you said, Sherry was going to talk about it. Can you say shortly how by from observation will we observe is not linear, how
Not completely. Okay, so in few words, so we take a map of galaxies in three-dimensional space. In fact, what we see is not really in three-dimensional space, as you will explain, but assume we have a map of galaxy in three-dimensional space. You smooth it over some scale, you reconstruct this Fourier spectrum. Then, in what we observe, typically, for the smallest value of k's corresponding to the largest wavelengths, we can still use the linear power spectrum, except that for some reason that she will explain, you have to multiply it by something called the bias factor. The bias factor does not depend on k on large scales. It means that up to a normalization, on large scale, small k, what you see is really this quantity. Nonlinear corrections are important for large k because, of course, at a given time in the evolution of the universe, there is a scale of nonlinearity. Okay? And this scale moves with time. At early time, the scale of nonlinearity is very small. Today, it has grown up to, it depends how you define it, but the order of 10 megaparsecs or so. And fortunately, we have data on scales much bigger than this. So the linear power spectrum is already an interesting quantity. Okay, so we are going first to think of a simplified universe where the density of baryons would be negligible with respect to that of CDM. And as a second step, we will add baryons. So we assume that omega b is much smaller than omega CDM. So if you want, baryons are like test particles. Okay, and delta matter in this case is roughly delta CDM. You want an equation of evolution for delta CDM. In order to compute such a master equation, you can combine the two equations of motion, the continuity and Euler equation for delta CDM. There are two first-order equations that you can transform in one second-order equation. Delta CDM is coupled gravitationally, so you will have metric fluctuations. So now you want to, if you want a master equation, you want to eliminate this metric fluctuation, term, and you do it using the Einstein equations. And in fact, the equation 0, 0 that I showed in the first course is sufficient. Okay, you are still left with some, with a critical density today, which appears in the final equation. And using the Friedmann equation, you eliminate it in favor of the scale factor. And after a little bit of work, but it's just combining linear equations, so it's nothing, you obtain the following master equation. Sorry? Sorry, yeah, perturbed Einstein equation. You are right. Perturbed Einstein equation. And so the two are 0, 0, perturbed and unperturbed. Minus 3/2 of A prime over A squared, omega CDM, that I take now as a function of time. It is density of CDM over total density at each given time. It's not the parameter defined today. Delta times delta CDM equal to 0. Okay, this is the master equation for linear structure formation, and we can interpret these terms. The last term is simply the one describing gravitational clustering. So this is gravity. If you reproduce all these steps, you will see that this comes from k squared psi, the gradient of the Newtonian potential. So this is really the gravitational force. And it tends to enhance, of course, the contrast density of cold dark matter. This is the Hubble friction term. What does it represent? Do you expect that gravitational collapse would take place at the same rate in a static universe and in an expanding universe? You don't, because gravitational forces come from 1 over squared distances. If all these distances are stretched by the expansion of the universe, it means that you slow down the effect of gravity. And this is exactly the physical meaning of this Hubble friction term. If you have more expansion, this is h. then the solution of the equation will correspond to slower structure formation.
Interesting, there's not only this equation directly counter gravity, it also gives gravity.
Yes. Yeah. Okay. If you apply this equation during radiation domination, then you have to work a bit more than during matter domination. During radiation domination, it's trivial to show that the scale factor goes like conformal time. This you can do. You take the Freeman equation, the definition of conformal time. This you can do in 1 minute. I encourage you to do it. During radiation domination, you have this relation, and omega CDM is very small, okay? Because the universe is dominated by photons. If I would take a 0 here, I would have a constant solution. That would end a decaying mode. That's not quite true. In fact, omega CDM cannot be neglected. It grows slowly with time, and when you do everything properly, you find that delta CDM grows during this stage logarithmically, like the logarithm of k eta. During matter domination, Friedman equation shows you that A grows like conformal time squared. And now things become easy because omega CDM could only be smaller than 1 if I would take into account for baryons. But I neglect baryons. And during matter domination, then I'm completely dominated by cold dark matter. This is 1. And then the solution is trivial. Delta CDM grows like eta square, or if you want, like the scale factor. This is something that you can also do as an exercise in 2 lines, taking this equation. So you see that structures form at a higher rate during matter domination than during radiation domination. It was expected from the beginning. During radiation domination, CDM are like test particles in a universe dominated by photons. So they cannot cluster very efficiently. During matter domination, they dominate the universe. So when they cluster, they enhance the gravitational waves. And the back reaction is that they cluster even more. They are like free-falling particles. And structure formation is much more efficient. Before I stop, I will make 2 remarks, and then we will go on tomorrow. The first remark is a very subtle point. You might say that I made a mistake in this step. Why? Because during radiation domination, I said this term comes from gravity. If I use the Poisson equation, the Laplacian of psi is equal to the total density perturbations. If I am during radiation domination, a priori, I cannot neglect the photons. So I should have another terms here. It should be coupled gravitationally with delta of the photons. A very subtle point has been understood by Weinberg, actually, and the best, if not the only place to read about this is Weinberg's book of cosmology that I actually wrote in the bibliography at the end of the lecture notes. When you take all species into account during radiation domination, you show that this equation is the correct one because there is no gravitational feedback of photons onto cold dark matter. This is really subtle. Okay, so at the end, I didn't make a mistake, but for a reason that I don't have time to explain. Okay. Last remark. During matter domination, this exact evolution, like proportional to the scale factor, which come exactly from this equation with 1 here and eta square in place of A, leads to a paradox. Let me write again, the Poisson equation in Fourier space. It looks like this. Okay. I am during matter domination. I'm considering only cold dark matter. So I can replace this by 4 pi j. Well, the first step is true anyway. I can replace this by the average density times the perturbation. Rho CDM during matter domination is essentially rho total. So I can use the Friedman equation and replace this by the A prime over A squared. But this is not what I wanted to do. We have enough here. Look. During matter domination, this scales like A to the minus 3. This scales like A to the minus 2, this factor. And we have just shown that this scales like A. How does psi scales? It's a constant. And it is something that we anticipated when we discussed the integrated Sachs-Wolfe effect, the late integrated Sachs-Wolfe effect. We said that there is no late integrated Sachs-Wolfe effect during matter domination because the potential is static. You have the proof. But it means that when structure form in the universe, the gravitational potential is a constant, while of course you would have expected it to grow with time, because you would have expected that gravitational potential will become deeper and deeper with time. This is really because you have these two antagonist effects of gravity and Hubble friction. By chance, during matter domination, there is like an exact cancellation between these two effects, resulting in a constant psi. There are models in which the growth rate of cold dark matter changes a little bit. If you have massive neutrinos or if you have early dark energy, you have a power here, a small negative power, meaning that the growth rate is a bit suppressed. As soon as the growth rate is a bit suppressed, psi will decay. And this is the case during lambda domination. During lambda domination, the growth rate is not anymore the same because you cannot use A grows like eta square. You find that the growth rate is slightly suppressed with respect to A, and hence psi will decay during that stage, explaining the late integrated Sachs-Wolfe. Okay, and I stop here for today. Thank you. Questions? Okay, so good pause.